Here we have the height of a tree, twice differentiable function. That's good language. That means it's smooth, it's continuous, it's differentiable, everything is good there. Part A says h prime of 6, you know, derivative is slope, so just go in between 5 and 7 where the 6 lies, and just write down the point, 5, 6, and 7, 11. Do your slope formula, subtract the y's on top, x's on the bottom, and it does say indicate the units, and it does say explain it in the context of that problem right there. So once you get that 5 halves, you know it's going to be meters per year. It's the derivative, how fast that's changing, and that means that t equals 6, the height of that tree is increasing at a rate of 5 halves meters per year. Okay, so we all know letter A, it's just an easy derivative. Letter B says explain why there must be. That sounds like a theorem talk all the way. And when I see derivative is equal to a number, I'm thinking mean value theorem right away. Please rewatch that theorem video if you're struggling with some of these theorems there. But just the very beginning of that video, I reteach these big theorems there. If you see the derivative is equal to a number, that's the mean value theorem. If you see the derivative is equal to 0, jot down Related's theorem. If you see the y value is equal to something like in between two other numbers, that's your intermediate value theorem right there. So here's what the mean value theorem says. If it has continuous and differentiable, so notice it told us it was differentiable, which means it's automatically continuous. So I just jotted down h is continuous and differentiable. And then if I can get that the slope between 2 points is equal to that too, then that means the derivative also has to be equal to 2. It just says the slope is equal to the derivative. So notice my work here. I tried the endpoints first. Like I tried the point 2, 1.5, 10, 15, but when I did that slope, I was like, well, hold up, that's not equal to 2 like we're supposed to. So then I had to look inside that interval and I had to kind of see where the slope was going to be 2. So I noticed that if I did 6 minus 2 and 5 minus 3, that would give me a slope of 2. So if you look at the point like 3, 2, and then 5, 6, and subtract the y's on the top, x's on the bottom, in between the 3 and the 5, that slope is equal to 2. And so if the slope is equal to 2, that's your f of b minus f of a over b minus a, and you have a continuous differentiable function, your derivative must also be equal to that. The mean value theorem guarantees that. So know the gist of those theorems, throw them down there right away, mention it's continuous and differentiable, and we're going to be good there. Letter C, trapezoidal sum. So Riemann sum is the rectangles, trapezoidal sum is area formulas of the trapezoid. Here is the area formula for a trapezoid. It helps me to draw a picture on the trapezoid there, but like if I ever have positive and negative values, I would probably just draw one picture and then try to use the pattern here. But if a picture helps you, go ahead. I'm talking about with the picture and with just the actual chart there once you get rolling. But if you just plot those dots real quick and you do the area of a trapezoid, it's like a trapezoid on its side. And so that's the top of it, that's the bottom of it. So those are the two bases. So if I do the area of that first one, I'll go base 1 plus base 2, that's 1.5 plus 2 divided by 2, and then I'll times it by the height. The height is just that little crevice right there in between 2 and 3, which is just equal to 1. So that's why I did the 1.5 plus 2 divided by 2 times by 1. When I do the area of the next one, I do 2 plus a 6 divided by 2 times it by 2 for the height of that thing. Now, once you get rolling with that, there is a pattern. Notice what we did here. If you do that without the picture, we did 1.5 plus 2. So I did this height plus this height. Those are my two bases divided by 2, and I times it by the distance between the 2 and the 3. And then I did the 2 plus the 6 divided by 2, times it by 2. And I did the 6 plus 11 divided by 2, times it by 2. And I did 11 plus 15 divided by 2, times it by the 3. And that's how I'm getting all of those numbers. Notice also it says the average height. So if it gives you a problem about cupcakes and talk about finding the average number of cupcakes, they're meaning for you to use your average value formula, which is this guy right here. And then the units will always be the same there. So it's going to be meters at the end of this thing. There's just the average height of that tree. So you know what an average is. It's sometimes it's going to be tall, sometimes it's going to be shorter, or just kind of growing up, not really shorter there, unless it gets hit by lightning or something like that. But yeah, it's just kind of growing up, so it's just going to be increasing there. But anyways, practice this without the calculator. Please do that. This is a no calculator problem. They did make those a little bit messier with some of these other problems and stuff there. So please practice that without the calculator. Do the old school arithmetic if you have to, and then just get that answer right there. And again, anytime you do your average value formula, the units will always be the same as the stuff that you're integrating. All right, letter D. Giant paragraph here. It looks intimidating, but this is not a difficult problem there. We could all handle this. They give us this function. This is the height of the tree. X is the diameter of the tree. And then when I start reading this, the tree is 50 meters tall. The diameter of the base of the tree is increasing at a rate of blah, 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 blah. And then find What's the rate of the change of the height of the tree with respect to time? This is a related rate problem. That's usually good news for us because typically when I see a related rate problem on the AP test, it's pretty straightforward there. So just convert your words to symbols like we did so well with in the past. It says when the G is the height, when the tree is 50 meters tall. So I wrote down G is equal to 50. The base, the diameter of the base, that's the X. They're telling us how fast the X is changing. That's dx dt in terms of the symbols there, meters per year. And we want to find out how fast the height's changing. That's how fast that G is changing. We want to find the dg, it sounds funky, dg dt, all right? We want to find that. All right, now, before you even do this, when we take this derivative here, see how it has x's in there? We're going to need an x in there. But then it tells us when the G is 50 meters tall. So when I'm 50 meters tall, I'm going to need to figure out what the x is equal to. So I took that 50, plugged it into that original function right there. And you see my work there. I just did a basic algebra problem, solved that, got x is equal to 1. I didn't do that until after I took this derivative and then realized, oh, darn, I don't have any G's in there to plug in that 50. I got X's in there. So you got to use the X that corresponds to when that G is equal to 50 there. Now, when you do the derivative, this is just a basic quotient rule. You do the denominator times the derivative of the numerator. But if you're doing the derivative of X's with respect to time, remember, you got to tag on the dx dt. Like, remember, if you have like y equals x squared, you go 2x dx dt. Same thing here. You got to tag on that dx dt, and you go minus the numerator times the derivative of the denominator, tag on the dx dt there over the denominator squared. And then you got to practice this, make this work in your brain without the use of that calculator right there. Please just practice that. I got like this is 200. Oh, what I saw here, I had a 0.03 there and a 0.03 there. So instead of trying to multiply by the decimals, I just factored out that 0.03 and I had my 200, I had my 100, and then the 100s even canceled out there. So then that was sweet. And I got that 3/4. And then we got the meters per year right there, how fast our height's changing. Bike paths.